what we're looking at here is, we will be looking at the arcsecant function. Now, the reciprocal functions, secant of x, cosecant of x, and cotangent of x are not always covered in depth, so many people are not familiar with their graphs. They have a distinct relationship to the functions of which they are the reciprocals. So secant of x has a distinctive relationship to the cosine graph, since they are reciprocals of each other. Reciprocation is a clearly defined and well understood relationship, and basically it works like this. Since you're taking a value and inverting it, literally switching numerator and denominator, we know that in a fraction, the bigger the numerator, the bigger the fraction, but the bigger the denominator, the smaller the fraction. So, it stands to reason that as a value gets larger and larger, its reciprocal gets smaller and smaller, or vice versa. So, with that in mind, what I have very faintly in here with a dashed line is the standard cosine graph. From this, we can get the graph of secant of x. So, there's a few important points to note. First of all, anytime cosine is 0, secant would have to be undefined, because 0 is the only number in existence that does not have a reciprocal, because you can't put 0 into the denominator. That actually gives us a familiar effect. Anytime cosine would be 0, secant would be undefined. I suppose you could ask, well, how do we know it's an asymptote and not, say, a whole? Well, that actually has to do with what the cosine graph is doing as it approaches 0. But there are going to be asymptotes in the secant function wherever cosine would be equal to 0. Now, from that, there's actually one other really nice value from cosine that we can use to reciprocate, or two actually, 1 and negative 1. 1 and negative 1 are unique among all numbers in that their reciprocals are those values. The reciprocal of 1 is 1, and the reciprocal of negative 1 is negative 1. So wherever cosine hits its peak or its valley, the secant graph will actually exist at that exact same point. So we start with the easiest points to nail down, the easiest characteristics. Now, that being said, in between, what we have are some less than friendly values for cosine, but easily interpretable. The cosine values from x equals 0 to x equals pi over 2, the x values are getting smaller and smaller and smaller, approaching 0. That means that its reciprocal should be getting larger and larger and larger, approaching its asymptote and going, well, infinite. We should then see, since the left side is actually doing the exact same thing, it's just doing it from right to left, we should see the same effect. That's really all we need to continue, because this entire portion here is exactly what this portion was, but with negatives. So from this point, if our values of cosine are getting smaller and smaller, just negative, then our values of secant should be getting larger and larger, but negative. And the same thing on this side. That is a single period of a cosine wave, and therefore this is a single period of secant. From there, the same way that cosine just repeats itself, secant just repeats itself. So secant has kind of this almost parabolic thing going for it. Not exactly parabolic, obviously, because of the asymptotes, but it's got this kind of U shape, like somewhat like a parabola, that comes down to meet cosine as cosine rises up to meet it, or comes up to meet cosine as cosine dips down to meet it. Now, obviously, this is not one-to-one. Like any of the trig functions, they are periodic. It's not one-to-one. The good news is, though, is the restriction is basically the same thing as the cosine graph. As long as cosine doesn't repeat its pattern of output values, then its reciprocals never repeat either. So, the restriction for cosine is never to go past its peak or its valley. Now, unlike the sine function, cosine does not start at 0 and then go up on one side and down on the other. So we still want to include the central point of x equals 0. But what that means is, since I can only go on the left side of that or the right side, I can't do both, I now have that choice that I alluded to in the video with the sine for arcsine, that we now have a choice. Do I take the left side of 0 or do I take the right side? Well, if you have the choice between negative values on the left and positive on the right, you pick positive. Positive x values are always going to be preferable. It tends to work out much better when you are inverting to deal with positives than to deal with negatives. It is possible to deal with negatives. It's just an extra hassle that really is kind of a difficult thing to work with. So for cosine, we go from this maximum down to this minimum, and then we stop. What that means for secant is that we're going to take the right branch of this U shape, but not the left, and the left branch of this upside down U shape, but not the right, because we're going to stop right there. Also, we do need to acknowledge the asymptote that's in the middle of that interval. So, let's talk about secant as a function. As always, the input is an angle measure in radians, always, for all trig functions, that is the case. The difference is the output value. Sine tells us a y-coordinate, cosine an x-coordinate, tangent tells us the slope of the terminal side. Secant of x is the reciprocal of the x-coordinate on the unit circle. Okay, so the domain of the secant function as it is, we actually have very much the same thing we had with tangent here, because tangent is sine over cosine, and secant is 1 over cosine. So they both have cosine in the denominator, and as such they have the same restrictions. Any place cosine is 0, we have the asymptote. So the domain of the secant function is actually the same as the domain of the tangent function. That x cannot be pi over 2 or any distance, any multiple of pi distance away from that. Now, however, as we saw, the restriction for cosine would be from 0 to pi. We do, however, need to acknowledge that in the middle of that is an asymptote. So, in order to make the secant function 1-to-1, we can go from 0 up to, but not including, pi over 2, and then a separate section after pi over 2, but not including it, all the way up to pi. So it's that same 0 to pi interval that cosine is restricted to, but excluding the pi over 2 in the middle of it. Now the range is interesting. If cosine is only allowed to be small, that means it had to be within one space of 0 either way. Then secant has to be more than one space either way. So the same way that the domain is broken up into different pieces like this, the range will be as well. So the range goes from -infinity up to -1, and then goes from 1 up to positive infinity, so that it's always larger in magnitude than 1, to correspond with the fact that cosine is always smaller in magnitude than 1. So, obviously, some unique kind of things going on here that you don't often see in most functions. So, the arcsecant function, the inverse secant. The inputs here will be the reciprocals of x coordinates on the unit circle. And the outputs will be angles in radians. So that we have that flip-flop effect from input and output between the original and the inverse. We get the same thing here. The range of the secant function becomes the domain of the inverse secant, or arcsecant. And the range of arcsecant is the domain under the restriction. And there we have the inverse secant, the arcsecant function.